From the smallest particles to structures spanning billions of light years, there is so much we still don't understand about our universe. How did it all begin? Are we alone in this infinite cosmic sea? Many such mysteries challenge and inspire us to look deeper into the cosmos, to hunt for the truth. Let's dive into a few of the strange phenomena, intriguing theories, and wild possibilities that could reshape our understanding of existence. The true nature of cosmic inflation. Was the universe always expanding? In the earliest moments of the universe's existence, there was a phase of extraordinary transformation. This period, referred to as cosmic inflation, was not merely an expansion, it was a surge of unimaginable proportions. The idea behind cosmic inflation suggests that the universe, in a fraction of a second, grew from something smaller than an atom to something larger than a galaxy. This rapid inflation is thought to have occurred right after the Big Bang, setting the stage for everything that followed. Cosmic inflation is an attempt to explain some of the biggest puzzles in cosmology. Why does the universe look so uniform on a large scale? Why do regions of the universe that are separated by vast distances share the same properties? Inflation provides an elegant answer. Before the universe expanded, everything was much closer together, allowing energy and temperature to even out. Then inflation stretched the universe so quickly that these regions ended up far apart. The standard picture of inflation is compelling, but it is far from the only theory. While many are familiar with the general idea of cosmic inflation, there are other models that push the boundaries of what we know. Among them, eternal inflation is one of the most fascinating and controversial. Eternal inflation takes the concept of rapid expansion and extends it indefinitely. In this model, inflation does not end everywhere at once. Instead, certain regions of space stop inflating, while others continue to expand. The regions where inflation stops can form pockets or bubbles of what we might call normal space, like the universe we live in. These pockets are where galaxies, stars, and planets can form. However, in the broader sense, the universe continues to inflate elsewhere, creating an endless network of expanding space and new pockets. This theory paints a picture of a multiverse, where each pocket is a universe with potentially different physical laws and constants. In our bubble, the conditions are just right for galaxies, stars, and life as we know it. But in other bubbles, the rules might be completely different. Some might have entirely different forms of matter, while others could be inhospitable to any form of life. If inflation never truly ends, is the universe infinite? And if there are countless other universes, what does that mean for our place in the cosmos? These are questions that scientists continue to wrestle with, using both mathematical models and observations of the cosmos. One of the challenges with eternal inflation is its speculative nature. It is a theory built on solid mathematical foundations, but it is difficult to test. Scientists look to the cosmic microwave background, or CMB, which is the faint glow left over from the Big Bang, for clues. This radiation carries imprints of the universe's earliest moments, including the effects of inflation. By studying patterns in this radiation, researchers hope to learn more about how inflation worked and whether it could be eternal. During the inflationary period, tiny random changes in energy occurred on a microscopic scale. As the universe expanded, these quantum fluctuations were stretched out, becoming the seeds of the large-scale structures we see today, like galaxies and clusters of galaxies. Without inflation, these structures might not exist. Quantum fluctuations also introduce the idea of randomness to the universe's formation, suggesting that some aspects of our cosmos may be the result of chance. While eternal inflation is one of the more exotic ideas, other models explore different aspects of the early universe. Some theories suggest that inflation was not a single event, but occurred in multiple stages, each with its own characteristics. Others propose that inflation could be cyclical, meaning the universe goes through repeated phases of expansion and contraction. One intriguing alternative is the idea of slow-roll inflation. In this model, inflation does not happen in an explosive burst, but unfolds more gradually. This theory provides a way to explain certain details of the universe's structure that standard models struggle with. Slow-roll inflation also offers a slightly different perspective on the role of quantum fluctuations, emphasizing how small changes in energy over time can shape the cosmos. Another proposal is the concept of hybrid inflation, which involves multiple fields of energy interacting to drive inflation. This model suggests that the process was more complex than a single field of energy expanding the universe. Instead, different forces might have worked together, each contributing to the overall expansion in unique ways. As scientists explore these models, they are also revisiting the assumptions behind inflation itself. One question that arises is whether the universe was always expanding. Inflation implies a rapid expansion, but what came before? Was there a time when the universe was static or contracting? Some theories suggest that the universe could have emerged from a previous phase, such as a collapsing universe or a state of high-energy equilibrium. These ideas challenge the traditional view of the Big Bang as a singular beginning, opening the door to new ways of thinking about the cosmos. Eternal inflation, slow-roll inflation, and other models are all attempts to answer the same fundamental questions. Why does the universe exist as it does? What mechanisms shaped its birth and growth? These theories are rooted in observations and mathematical models that seek to describe the universe's history. But the full story of cosmic inflation remains elusive, a puzzle that continues to inspire and challenge the scientific community. Dark matter's role in shaping the early universe. Still a mystery. In the early days of the universe, after the rapid expansion of cosmic inflation had settled, a new stage of transformation began. This was a time when the universe was still incredibly hot and dense, but it was beginning to cool and spread out. As this happened, the forces of nature started shaping the cosmos into what we recognize today. Among these forces was something mysterious and unseen: dark matter. Dark matter is a term that scientists use to describe a strange, invisible substance that doesn't emit light or energy. It can't be seen directly, but its presence is known because of the way it affects gravity. Without dark matter, the universe would look very different. Galaxies, for example, might never have formed, and the cosmic structures we see today would not exist. The story of dark matter begins shortly after the Big Bang. As the universe expanded and cooled, particles began to come together to form the first atoms. But even before that, dark matter was already at work. It created invisible scaffolding, a kind of cosmic framework around which ordinary matter could gather. Without this framework, the pull of gravity from ordinary matter alone would have been too weak to bring particles together quickly enough to form galaxies and stars. Dark matter's role in the formation of galaxies is one of the most intriguing parts of its story. Scientists believe that dark matter clumped together in the early universe, forming dense regions called halos. These halos acted like gravitational wells, pulling in ordinary matter, mostly hydrogen and helium gas. Over time, this gas condensed and ignited, giving birth to the first stars and galaxies. The process was slow and took millions of years, but without dark matter, it might not have happened at all. Dark matter doesn't interact with light or any other form of electromagnetic radiation. This makes it invisible, even to the most advanced telescopes. Scientists have tried to detect dark matter directly using underground experiments designed to pick up any interaction it might have with ordinary matter. But so far, these efforts have come up empty. Despite this, the gravitational effects of dark matter are clear. Galaxies spin faster than they should if they were made of ordinary matter alone, and clusters of galaxies are held together by far more gravity than visible matter can explain. There are many theories about what dark matter might be. Some scientists think it could be made of particles that we haven't discovered yet, such as axions or WIMPs, aka weakly interacting massive particles, which are hypothetical particles that would explain some of the strange behaviors of the universe. Others propose that dark matter could be something entirely different, such as primordial black holes left over from the early universe. Dark matter also influences how galaxies behave and interact with one another. When two galaxies collide, their dark matter halos can merge, creating a gravitational pull that shapes the resulting galaxy. Dark matter also affects the way galaxies move within clusters. Observations of galaxy clusters show that the visible matter alone isn't enough to explain the speeds at which galaxies move. Dark matter provides the extra gravitational force needed to account for these motions. There are some theories that challenge the existence of dark matter altogether. These alternative ideas propose that the strange behaviors we see in galaxies and clusters could be explained by modifying the laws of gravity. One such theory is called MOND, or Modified Newtonian Dynamics, which suggests that gravity behaves differently on large scales than it does on smaller ones. While these ideas are intriguing, they have not been able to explain all the evidence as well as the dark matter hypothesis. The search for dark matter is ongoing and has led to some of the most ambitious experiments in physics. Underground detectors, space-based observatories, and particle accelerators like the Large Hadron Collider are all being used to look for signs of dark matter particles. Scientists are also studying the behavior of stars and galaxies in detail, hoping to find indirect evidence of dark matter's effects. Every new piece of data brings us closer to understanding this mysterious substance, but it also reminds us of how much we still don't know. Baryon asymmetry. Why does matter dominate over antimatter? The universe is filled with matter. Stars, planets, and even ourselves are all made of it. But the existence of matter at all is a profound mystery. According to what we know about physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of energy. If the amounts were truly equal, the universe would have been left with nothing but light, with no atoms to form galaxies, stars, or life. Yet somehow, matter won out. This imbalance, known as baryon asymmetry, is one of the most puzzling questions in science. Baryons are particles like protons and neutrons, the building blocks of ordinary matter. Their antimatter counterparts, such as antiprotons and antineutrons, have the same mass but opposite charge. In theory, the Big Bang should have been symmetrical, creating baryons and antibaryons in perfect balance. But the fact that the universe exists at all shows that something tipped the scales, leaving us with more matter than antimatter. To explain this imbalance, scientists have turned to a variety of hypotheses. One of the most promising ideas involves a phenomenon known as CP violation. CP stands for charge parity, two fundamental properties of particles. Charge refers to whether a particle is positively or negatively charged, while parity describes how a particle behaves when its spatial coordinates are flipped, like looking at it in a mirror. In most cases, the laws of physics treat particles and antiparticles symmetrically. This means that if you swap a particle for its antiparticle and reverse its spatial coordinates, the physics should remain unchanged. However, experiments have shown that this symmetry doesn't always hold. CP violation was first observed in the 1960s in experiments involving particles called kaons. Kaons are unstable particles that decay into other particles over time. Scientists found that kaons and their antiparticles did not decay in exactly the same way, breaking the symmetry between matter and antimatter. This discovery was groundbreaking because it provided a mechanism that could help explain why matter came to dominate the universe. Later experiments revealed CP violation in other particles, such as B mesons, which are also short-lived and decay into lighter particles. These findings confirmed that the laws of physics are not perfectly symmetrical and that there are processes in the universe that treat matter and antimatter differently. However, the amount of CP violation observed so far is not enough to fully explain the imbalance between matter and antimatter. This suggests that there may be other sources of CP violation that we have not yet discovered. Another hypothesis involves the early universe's extreme conditions. During the first fractions of a second after the Big Bang, the universe was incredibly hot and dense. In this environment, particles and antiparticles were constantly being created and destroyed. As the universe expanded and cooled, these processes slowed down, and the remaining particles and antiparticles began to annihilate each other. If there was even a tiny asymmetry in the number of particles and antiparticles to begin with, it could have left a small excess of matter. Over billions of years, this small imbalance would have grown to form the matter-dominated universe we see today. Some suggest that this asymmetry could have been caused by interactions involving particles that no longer exist. For example, certain grand unified theories propose that heavy particles called X bosons, which may have existed only in the earliest moments of the universe, could have decayed in ways that favored matter over antimatter. These particles are purely theoretical and have not been observed, but their existence would provide a natural explanation for baryon asymmetry. Another area of research focuses on leptogenesis, a process involving neutrinos. Neutrinos are incredibly light, almost ghost-like particles that barely interact with ordinary matter. Some theories suggest that heavy versions of neutrinos, which might have existed in the early universe, could have decayed in ways that produced more matter than antimatter. These heavy neutrinos are also hypothetical, but their behavior could explain not only baryon asymmetry, but also why neutrinos have such small masses compared to other particles. The conditions of the early universe cannot be directly recreated, and the particles involved may be far beyond the reach of current experiments. However, scientists are using advanced particle accelerators, such as the Large Hadron Collider, or LHC, to search for signs of new particles and interactions that could shed light on these processes. Experiments are also being conducted to study neutrinos in greater detail, with the hope of uncovering clues about their role in the universe's asymmetry. Despite decades of study, baryon asymmetry remains a deep and enduring mystery. The existence of matter itself is a testament to some hidden mechanism that tipped the balance in favor of matter over antimatter. Understanding this mechanism is a quest to understand why the universe exists in its current form and why we are here to observe it. Planet 9, a myth or a hidden giant. Far beyond the familiar planets of the solar system lies a region shrouded in mystery. The Kuiper Belt, a vast expanse of icy objects and dwarf planets, stretches out past Neptune, marking the edge of the known solar system. Among the countless small bodies in this distant realm, some scientists believe there might be a giant hiding, a massive, unseen planet often referred to as Planet 9. The idea of Planet 9 first gained attention in 2016, when astronomers noticed something strange about the orbits of certain objects in the Kuiper Belt, a region beyond Neptune that is populated with icy bodies and dwarf planets. These objects, known as trans-Neptunian objects, have elongated, tilted orbits that seem to cluster together in a way that is hard to explain. Normally, the orbits of such distant objects would be spread out randomly, influenced by the gravitational pull of Neptune and other nearby planets. But the clustering pattern suggested that something much larger might be exerting its influence from afar. The hypothesis is that Planet 9 could be a massive planet, about 5 to 10 times the mass of Earth, located hundreds of times farther from the Sun than Earth. Its gravity, even from such a great distance, could explain the unusual orbits of these trans-Neptunian objects. If it exists, Planet 9 would be a frozen world, receiving only a faint amount of sunlight, making it incredibly difficult to detect. Astronomers have been using powerful telescopes to scan the skies for any sign of the hidden planet. They also rely on computer simulations to model how such a planet might interact with other objects in the solar system. These simulations show that a planet of the proposed size and distance could indeed produce the clustering effect observed in the Kuiper Belt. Despite the intriguing evidence, not everyone is convinced that Planet 9 exists. One argument against it is that the clustering of trans-Neptunian objects might not require a giant planet at all. Some researchers suggest that the pattern could be a statistical fluke caused by the small number of objects observed so far. Others propose that the clustering could result from the combined gravitational effects of many smaller objects in the Kuiper belt rather than a single massive planet. If the planet is as far away as the models suggest, it would appear incredibly faint in the sky, even with the most advanced telescopes. Its motion would also be very slow, making it hard to distinguish from background stars. Astronomers have been searching for years without success, but the possibility of finding such a significant addition to the solar system keeps the hunt alive. The idea of hidden planets is not new. In the past, astronomers have searched for unknown planets based on irregularities in the orbits of known ones. In the 19th century, the discovery of Neptune came about in a similar way, after scientists noticed that Uranus's orbit was being perturbed by an unseen force. Later, the search for another hidden planet led to the discovery of Pluto, although Pluto turned out to be far too small to account for the observed effects. Planet 9, if it exists, would not be the only unusual feature of the outer solar system. The region is home to a variety of oddities, including Sedna, a dwarf planet with an orbit that takes it incredibly far from the Sun. Sedna's orbit is so elongated that it cannot be explained by the gravitational pull of the known planets alone. Some scientists think that Planet 9 could be responsible for shaping Sedna's path. There are also theories that Planet 9 could have formed closer to the Sun and been pushed outward over time. This could have happened if the early solar system was a chaotic place, with planets jostling for position and interacting gravitationally. In this scenario, Planet 9 might have been flung to the outskirts of the solar system during a close encounter with Jupiter or Saturn. Alternatively, it could be a captured rogue planet, a wandering body that was pulled into the Sun's orbit after drifting through interstellar space. The potential discovery of Planet 9 would have profound implications for our understanding of the solar system. It would challenge existing models of planetary formation and migration, shedding light on the processes that shaped the early solar system. It could also provide clues about the conditions in the outer reaches of the Sun's influence, where the boundary between the solar system and interstellar space begins to blur. The enigma of Oumuamua, natural object or alien technology. In October 2017, a mysterious object streaked through our solar system. It wasn't like anything we had seen before. The object, named Oumuamua, which means scout or messenger in Hawaiian, was the first interstellar object ever detected passing through our solar system. While many natural objects like comets and asteroids routinely visit our solar system, Oumuamua's characteristics were far from typical. Its origins, its strange behavior, and even its shape sparked a whirlwind of debate among scientists. At first glance, Oumuamua appeared to be a simple asteroid or comet, but the more astronomers observed it, the more unusual it became. The object was an elongated, cigar-shaped object, measuring about 800 meters long and only about 80 meters wide, remarkably thin for its size. What immediately puzzled researchers was how it seemed to be accelerating as it moved through space. As it traveled away from the Sun, it was moving faster than it should have been, based on gravitational influences alone. It wasn't unusual for an object to accelerate due to the Sun's gravity, but Oumuamua was speeding up in a way that couldn't be explained by just this. As comets approach the Sun, the heat causes their icy surfaces to vaporize, releasing gas and dust in a process called outgassing. This creates a push that can alter the object's trajectory, helping explain any unusual acceleration. But Oumuamua did not exhibit the typical signs of outgassing. It didn't have a visible tail or coma, characteristics that would be expected if it were a comet. Its lack of gas emissions was odd, given that it was speeding up in a way that normally requires some kind of propulsion. This led some scientists to propose more speculative ideas, including the possibility that the object might not be natural at all. Some suggested that Oumuamua could be an interstellar probe, an artificial object sent from another star system. This idea gained popularity in part due to the object's shape. The elongated, thin form of Oumuamua was unlike anything seen before in our solar system. Most asteroids and comets are irregularly shaped, but Oumuamua appeared to be unusually long and flat. This strange geometry led to suggestions that it might be a probe sent by an advanced civilization, traveling across the cosmos in search of signs of life or resources. Another possibility raised by some scientists was that Oumuamua could be some kind of light sail, a technology used to propel spacecraft using the pressure of light from stars. A thin, flat object like Oumuamua could theoretically be propelled by radiation pressure, which is the force exerted by light as it strikes an object. If it were a light sail, the object might have been deliberately sent out on a mission by an alien civilization. This idea was fueled by the object's acceleration, which seemed to match the behavior of an object propelled by light pressure, rather than gravitational forces alone. These theories gained even more attention after Harvard astronomer Avi Loeb made waves with his book, Extraterrestrial, where he argued that Oumuamua's unusual behavior and properties pointed to the possibility that it could indeed be an artificial object. Loeb suggested that the object might be a thin sheet of metal, possibly discarded debris from an alien spacecraft or probe. He even raised the possibility that it could have been deliberately directed toward our solar system as part of an interstellar mission. However, the idea that Oumuamua is a probe has been met with significant skepticism. Many astronomers argue that the object's behavior can be explained without invoking extraterrestrial origins. Some propose that it could simply be a natural object, but one with very unusual properties. One idea is that Oumuamua could be a fragment of a larger body that was ejected from a distant star system. Over time, the object could have been spun up, possibly due to interactions with a nearby star, leading to its strange elongated shape. Another natural explanation is that Oumuamua could be a type of comet, but one made mostly of metal instead of ice. In this scenario, it would have behaved much like a comet in terms of acceleration, but without the typical outgassing effects seen in icy comets. The unusual lack of visible tail could be explained if the object were composed of materials that don't easily vaporize when heated by the sun. This could account for both the mysterious acceleration and the lack of a visible coma, as there wouldn't be any gas or dust to form a tail. Some also suggested that the object's strange behavior might be a result of it tumbling as it traveled, with its shape and rotation causing uneven radiation pressure and acceleration. More recent observations and analyses have added to the mystery, but they have not provided a clear answer. Since its discovery, astronomers have not been able to spot any other objects like Oumuamua, which raises the question of whether it is a rare and unique anomaly or just a member of a larger class of objects that we haven't yet detected. While some astronomers have continued to search for other similar objects, others argue that Oumuamua's strange properties are simply the result of random natural processes that are poorly understood. Regardless of whether Oumuamua is a natural object or something more extraordinary, its passage through our solar system has had a profound impact on the scientific community. The object has spurred new discussions about the possibility of interstellar travel, both by natural objects and by artificial probes. The puzzle of Saturn's hexagonal storm, natural phenomenon or something else. Saturn, the majestic gas giant, is home to many awe-inspiring features. Among its most puzzling attributes is a vast storm system located at its northern pole. This storm, which has become iconic in its own right, is unlike any other storm we've encountered in the solar system. It forms a perfect six-sided hexagon, a geometrical pattern that defies simple explanation. The hexagonal storm has been a subject of fascination ever since it was first observed by the Voyager spacecraft in the early 1980s, and later by the Cassini mission, which spent years studying the planet up close before it was concluded in 2017. At first glance, one might assume the hexagonal shape is just a quirk of nature, a rare but not entirely impossible formation. After all, nature is often capable of producing surprising shapes and patterns. But as scientists examined Saturn's hexagonal storm more closely, they found that it didn't behave like a typical storm system. The storm is unusually stable, remaining intact for decades, and it stretches some 30,000 kilometers across, about 20 times the diameter of Hurricane Katrina. The storm sits at Saturn's North Pole, where the winds swirl in a counterclockwise direction. The hexagon, with its sharp corners and straight edges, seems almost artificially constructed. A geometric shape like this seems impossible in a natural fluid system. After all, we rarely see sharp corners in the chaos of weather systems here on Earth. The shape of storms in our atmosphere is typically dictated by the surrounding environment, with circular or spiral patterns taking over. But Saturn's storm is not only a geometric anomaly, it also exhibits some extremely interesting behavior. The storm rotates with an odd sense of symmetry, with the 6 sides of the hexagon maintaining their form even in the face of dramatic shifts in Saturn's atmospheric conditions. One theory proposed to explain this strange formation involves the nature of Saturn's atmosphere itself. Saturn is a gas giant, which means it has no solid surface like Earth. Its atmosphere consists mainly of hydrogen and helium, with trace amounts of other gases. Saturn's winds are also incredibly strong, reaching speeds of up to 1,800 kilometers per hour, or about 1,100 miles per hour. This kind of wind, combined with the planet's low temperatures and lack of solid boundaries, makes its atmosphere behave very differently from Earth's. Saturn spins incredibly fast on its axis, once every 10 hours and 33 minutes, causing a phenomenon known as differential rotation, where different parts of the atmosphere move at different speeds. Scientists have suggested that the swirling winds in Saturn's atmosphere create a kind of fluid dynamic effect that could lead to the formation of a polygonal storm like the hexagon. Essentially, the rotation of Saturn might create waves in the atmosphere that form stable, repeating patterns, with the 6 sides of the hexagon emerging as a natural consequence of how the atmosphere behaves under certain conditions. But while this idea might explain some of the storm's behavior, it still doesn't fully address why the hexagon remains so perfectly shaped. After all, in nature, perfect geometric patterns like this are extremely rare, especially when considering the size and scale of the storm. The storm's sharp corners and distinct straight edges seem almost too deliberate to be an accident of nature. Some have proposed that there might be something about the unique properties of Saturn's atmosphere that helps sustain this strange shape. For instance, the hexagon could be a result of the way the planet's fast rotation affects the dynamics of the upper atmosphere. The upper layers of Saturn's atmosphere might experience forces that guide the winds into forming a 6-sided structure, like ripples in a pond that align in symmetrical patterns. Such patterns are not unheard of in other fluid systems, like those found in lab experiments with rotating fluids, where vortices can sometimes form into polygons. This suggests that the hexagon might be the result of some kind of fluid dynamics, although we still don't fully understand the details. Another theory takes inspiration from a more terrestrial example: the formation of hexagonal basalt columns on Earth. These striking formations, which can be found in places like the Giant's Causeway in Ireland, are formed when lava cools and cracks into hexagonal shapes. The idea is that the hexagonal pattern in Saturn's storm might be a result of similar physics at work, except instead of lava, it's the atmosphere itself cooling and shifting, causing it to settle into a stable, repeating pattern. However, the hexagonal columns on Earth form under solid conditions, and Saturn's atmosphere is fluid and constantly in motion, making this analogy somewhat difficult to apply in its entirety. More recently, scientists have been exploring how the unusual temperature differences between the upper and lower layers of Saturn's atmosphere might contribute to the hexagon's stability. At Saturn's poles, there is a noticeable difference in temperature between the upper and lower layers of the atmosphere. In the lower atmosphere, the temperature is much warmer, while in the upper layers the temperature is much colder. This temperature gradient could cause the winds to behave in a specific way that helps maintain the hexagonal shape. Saturn's hexagon could be influenced by long-lasting atmospheric waves that propagate through its atmosphere. These waves, which are thought to occur in the upper atmosphere, might interact with the planet's internal dynamics in such a way that they create a stable, six-sided pattern. These waves could be similar to the standing waves observed in some fluid dynamics experiments, where oscillations create stable patterns in a rotating fluid. Despite the many theories, there is still no consensus about what exactly causes the hexagon. The unusual behavior and the complexity of the interactions involved make it a difficult puzzle to solve. While scientists can experiment with fluids in laboratories, they cannot easily replicate the extreme pressures, temperatures, and rotational speeds found on Saturn. As a result, much of the research is based on computer models, which are often limited by the assumptions made about how Saturn's atmosphere behaves. The solar system's missing planets, evidence of a chaotic early history. The solar system, with its 8 planets neatly orbiting the Sun, may seem like a stable, well-organized system. But when we peer into its past, things weren't always so orderly. Evidence suggests that during its early history, the solar system might have been far more chaotic. Planets, or what could have been planets, may have been lost, ejected, or collided in ways that left behind the familiar configuration we see now. Over the course of billions of years, interactions between these early planets, the Sun, and other objects in the solar system could have shaped it into the structure we recognize today. The current alignment of the planets suggests a system that has settled into a relatively calm state, but this was not always the case. For example, the presence of the asteroid belt between Mars and Jupiter suggests that at one time there may have been a planet in that region, or at least an object large enough to have formed a planet. However, something happened to disrupt that formation, and the asteroid belt was left as a scattered collection of smaller rocks and debris. In the outer solar system, some suggest that there might have once been more planets beyond Neptune that were either ejected from the solar system or lost in some other way. Evidence for this comes from the unusual orbits of objects in the Kuiper belt. Many of the objects in this region have highly eccentric orbits, which suggests that they may have been disturbed by a massive planet or multiple planets that once existed further out. One of the most well-known models to explain the missing planets is the idea of a chaotic early solar system. According to this theory, in the first few 100 million years of the solar system's existence, the planets didn't follow stable orbits. Instead, they were in a much more chaotic state, with gravitational interactions between them causing frequent collisions, ejections, and migrations. In this early period, planets could have been kicked out of the solar system entirely, while others may have collided with each other or merged into larger bodies. Studies of the solar system's formation suggest that Jupiter and Saturn likely formed closer to the Sun and then migrated outward to their current positions. According to the Grand Tack hypothesis, Jupiter originally formed closer to the Sun, but then, due to interactions with Saturn, moved outward. As it migrated, it caused disruptions in the orbits of nearby planets and objects. Jupiter's migration is thought to have tacked inward, akin to a sailboat as it sails against the wind, causing a period of instability that may have led to the loss of some planets or the ejection of smaller objects from the solar system. The discovery of objects like Sedna, an icy body far beyond Pluto, suggests that the solar system may have once been much larger, with more objects in its outer reaches. The orbit of Sedna is highly elongated and tilted, which suggests that it was likely influenced by a massive planet or multiple planets that once existed beyond Neptune. Another important piece of evidence comes from the study of the Oort cloud, a vast and distant region that is thought to contain billions of icy bodies. The Oort cloud is located far beyond the orbit of Pluto, and many of its objects have been influenced by gravitational interactions with other stars or objects in the galaxy. Some theories suggest that the Oort cloud could be the remnants of a much larger solar system, with planets that were once part of the system but were ejected during the early chaotic period. These ejected planets could have been sent on orbits that took them far away from the Sun, leaving behind only the icy bodies of the Oort cloud. One of the key questions in the study of the missing planets is whether these lost worlds were once massive enough to be classified as planets, or if they were smaller bodies that were disrupted and lost over time. It's also unclear whether these planets could have formed in the same way that the current planets did. In the traditional model of planet formation, planets form from the gradual accumulation of dust and gas in a protoplanetary disk. However, the chaotic early solar system suggests that planet formation may not have followed this neat, predictable process. Instead, large bodies could have formed in unexpected places, only to be disrupted by the migration of Jupiter and Saturn. The solar system we know today is the result of billions of years of cosmic processes, many of which we are still trying to fully understand. The missing planets may never be found, but their story continues to shape our understanding of how the solar system came to be. The faint Fermi bubbles, clues to the galaxy's violent past? The Milky Way is a vast and dynamic system, but not everything within it is easy to observe. Some of its most intriguing features are hidden from view or faintly visible, often requiring special instruments to detect. One such feature, discovered only in recent years, is the Fermi bubbles, a pair of enormous structures of gamma-ray emission that extend far above and below the plane of the galaxy. The Fermi bubbles were first detected in 2003 by NASA's Fermi Gamma-Ray Space Telescope, which was designed to study high-energy phenomena in the universe. The telescope was looking at the center of the Milky Way, where the activity of the supermassive black hole is known to influence the surrounding environment. What scientists noticed was an unusual pair of structures extending about 25,000 light-years above and below the galactic plane. These structures, shaped like gigantic bubbles, emit powerful gamma rays. Their discovery raised a lot of questions. What could be the source of this intense gamma radiation? And why do these structures seem to stretch so far from the galactic plane? One of the leading explanations is that the bubbles are the remnants of an outburst or series of explosive events from the supermassive black hole at the center of the Milky Way, known as Sagittarius A*. Supermassive black holes are known to have periods of intense activity, during which they can expel vast amounts of energy and matter into space. This process, known as active galactic nucleus, or AGN, activity, can produce powerful jets of particles and radiation, which may have created the Fermi bubbles. The bubbles are symmetrical, with their centers aligned with the position of the supermassive black hole, and they exhibit high-energy gamma rays that are consistent with what one would expect from an AGN explosion. These outbursts could have occurred millions of years ago, during a time when the supermassive black hole was more active and was releasing enormous amounts of energy. This energy would have blasted outward, creating the bubbles we see today. These structures are massive and extend well beyond the region of the galaxy where most stars and nebulae are found. To put this into perspective, the bubbles span a distance that is roughly equivalent to the entire diameter of the Milky Way. This immense scale suggests that the events responsible for their creation were incredibly powerful, releasing vast amounts of energy that shape the surrounding space. The fact that these bubbles are still visible today, after millions of years, highlights the lasting impact of these outbursts on the galactic environment. While the black hole outburst is the leading explanation, there are still some mysteries surrounding the Fermi bubbles. For one, the bubbles' gamma-ray emissions don't completely match the typical patterns expected from a black hole outburst. Some of the radiation appears to be coming from regions outside of the bubbles themselves, which suggests that there may be additional processes at work. It's possible that the material surrounding the supermassive black hole could have been heated to extremely high temperatures during the outburst, and that this radiation has been scattered and diffused across a larger area. Other theories propose that the bubbles may have been caused by the interaction between high-energy cosmic rays and the interstellar gas, which could result in the emission of gamma rays. Some scientists suggest that the Fermi bubbles could be connected to the cosmic ray population of the galaxy. Cosmic rays are high-energy particles, primarily protons, that travel through space at nearly the speed of light. These are believed to come from a variety of sources, including supernova explosions, black holes, and other high-energy phenomena. The outbursts from the supermassive black hole may have accelerated particles to extremely high speeds, creating the cosmic rays that we detect today. The discovery of the Fermi bubbles has opened up new avenues of research into the violent processes that shape galaxies. It's believed that active galactic nuclei, like the one at the center of the Milky Way, are an important factor in regulating the growth and development of galaxies. The energy released by these black holes can influence the surrounding gas and stars, affecting the rate of star formation and the distribution of matter within the galaxy. The Fermi bubbles may be a direct consequence of this process, providing a snapshot of the kind of energetic events that occur in the heart of a galaxy. In the early universe, supermassive black holes were more active, and their outbursts may have been more common. The Fermi bubbles may be a relic of these early, more violent times, offering a glimpse into the past of our galaxy and other galaxies like it. In fact, the Fermi bubbles are not unique to the Milky Way. Similar structures have been observed in other galaxies as well, suggesting that these outbursts are a common feature of galactic evolution. New observations from advanced telescopes like the James Webb Space Telescope are likely to provide more detailed information about these enigmatic structures. Zoo hypothesis. Are we being watched by advanced civilizations? Despite the enormous size of the cosmos and the billions of planets that could potentially harbor life, the search for extraterrestrial intelligence has yielded little more than silence. This has led to a number of theories to explain the lack of contact with alien civilizations. One such theory is known as the zoo hypothesis, which suggests that we are not being ignored by advanced extraterrestrial civilizations, but rather we are being deliberately avoided. According to this hypothesis, these civilizations are aware of our existence, but they choose not to make contact, much like zookeepers observing animals in a zoo from a distance. The zoo hypothesis presents a fascinating thought experiment. What if there are intelligent civilizations out there, far more advanced than ours, who are monitoring us but are intentionally refraining from making themselves known? The premise is rooted in the idea that more advanced civilizations would have developed technologies so powerful that they could easily observe us, but they may choose not to interfere with our natural development. This could be for a variety of reasons, from ethical concerns about disrupting a developing civilization to the belief that contact with us would not be beneficial for either party. The vast number of stars in the Milky Way galaxy alone, roughly 100 billion, each with potentially habitable planets orbiting them, suggests that the odds of intelligent life emerging somewhere else in the universe are incredibly high. Yet, after decades of searching, we have found no direct evidence of alien civilizations. The silence we observe could be explained by the idea that advanced civilizations are deliberately avoiding detection, perhaps following some form of intergalactic code of conduct that prevents them from interfering with less advanced species. There are a number of possible motivations for such behavior. One explanation is that advanced civilizations may follow something akin to a prime directive, a concept popularized in science fiction, particularly in shows like Star Trek. The idea is that higher civilizations may have come to the conclusion that intervening in the development of less advanced species can be harmful. By observing us from a distance without making direct contact, they allow us to evolve naturally, without external influences that could alter the course of our development. In this scenario, our development as a species would be seen as a sort of experiment, with advanced civilizations acting as passive observers rather than active participants in our history. Another reason why they might avoid contact is that they may view us as dangerous or unpredictable. They might see us as an immature species with the ability to destroy ourselves with our growing technological capabilities. The fear could be that contact with us might trigger an escalation of violence or result in our species making destructive choices that could affect the broader galaxy. By staying in the background, These civilizations might be hoping that we will reach a level of maturity and wisdom where we can make peaceful contact on our own terms without the risks associated with interference. This idea aligns with a broader concept known as the Great Filter, which posits that there may be some kind of universal obstacle that prevents intelligent civilizations from reaching the level of technological development that would allow for interstellar communication or travel. The Great Filter could be something that is difficult for a species to overcome, such as self-destruction or the inability to survive long enough to develop advanced technologies. If this theory holds true, the lack of contact with extraterrestrial civilizations could be a sign that we are in the early stages of our development and that we must prove our ability to survive and mature before we are allowed to join a galactic community. If aliens are intentionally avoiding us, then the lack of extraterrestrial signals or any signs of their presence makes sense. Perhaps these civilizations have set up protocols to avoid detection by primitive species like ours. They may be employing advanced forms of communication that we cannot yet detect, or even conceiving of ways to hide their presence entirely from our sensors. Perhaps just as humans study the natural world using tools like telescopes and microscopes, it is possible that more advanced civilizations have developed methods of observation that are beyond our current understanding. They might be able to observe our planet, our society, and even our thoughts without leaving any traces of their presence. They could be utilizing technologies so advanced that any attempts on our part to detect them would be futile. An implication of the zoo hypothesis is the idea that we may be in a sort of waiting room for first contact. If advanced civilizations are deliberately withholding contact with us, we could be left in a state of isolation until we prove that we are ready for such an encounter, which then raises the question of what it would take for us to earn the right to make contact with these civilizations. Would we need to achieve certain technological milestones, such as mastering interstellar travel or communication, before they would allow us to join the galactic community? Or would it be a matter of proving that we are capable of peaceful coexistence and responsible stewardship of our own planet? If there are alien civilizations observing us, do they have an ethical responsibility to intervene if we are headed towards self-destruction? Could they allow us to continue down a path of war, environmental destruction, or societal collapse, simply because they have chosen not to interfere? Conversely, there could be a kind of moral wisdom in withholding contact, allowing a species to develop on its own terms and avoid the dangers of premature intervention. We watch animals in their natural habitats, often from a distance, trying not to disturb their behavior or alter their environment. In some cases, we protect endangered species, but we do so with a careful, hands-off approach. If there are extraterrestrial civilizations watching us in a similar manner, they may view us not as something to be dominated or controlled, but as a species with the potential for growth and development as long as we are left to our own devices. Time crystals. Could they rewrite our understanding of time? In 2012, a new concept that seems straight out of science fiction was introduced in the realm of physics: time crystals. Unlike anything scientists had ever encountered before, time crystals suggested that it might be possible to have a phase of matter that defied the usual understanding of time and energy. At first, the idea sounded impossible, but in recent years, breakthroughs have shown that these strange theoretical structures can indeed exist under the right conditions. Time crystals are now becoming one of the most exciting and mysterious phenomena in modern physics, offering tantalizing possibilities for pushing the limits of what we know about the universe. Most forms of matter, like solids, liquids, and gases, are based on certain patterns of energy or arrangement of particles. These phases of matter exist in a stable state, where the particles in the material are either static, like a solid, moving past each other, like a liquid, or moving freely, like a gas. What sets time crystals apart is that they are not static in space, nor are they conventional materials that you can touch and feel. Time crystals appear to be in perpetual motion, but in a way that violates the usual laws of physics. This kind of behavior, where the system oscillates between states without losing energy, is sometimes called time translation symmetry breaking. Typically, physical systems tend to settle into an equilibrium, where everything comes to rest after a certain period. In the case of time crystals, instead of reaching equilibrium, the system enters a sort of perpetual state of oscillation, where its internal structure continuously repeats itself over time. This oscillation is not driven by an external energy source. Instead, the system's behavior is self-sustaining. This means that the time crystal is effectively ticking without expending energy, a feat that would seem to defy the second law of thermodynamics, which tells us that systems tend to lose energy over time and eventually reach equilibrium. The breakthrough came when researchers realized that time crystals could be created in a lab using quantum systems. In 2016, a team of physicists from the University of Maryland and Harvard University announced that they had managed to create a time crystal using qubits, quantum bits of information that are the building blocks of quantum computers. These qubits are able to exist in multiple states simultaneously, a property known as superposition, which allows for a unique form of time crystal to emerge. In their experiment, the qubits were arranged in a way that allowed them to oscillate between two states of energy in a periodic fashion, effectively creating a time crystal. The idea behind this is that the qubits, instead of settling into a state of equilibrium, constantly flip between two distinct states, essentially ticking in time like a clock. The motion of the qubits wasn't being driven by an external force, but was instead a natural outcome of the quantum interactions taking place within the system. The result was a material that, while not directly observable to the naked eye, exhibited time-based symmetry breaking in a lab setting. Normally, time is treated as a linear, unidirectional force that flows from the past to the present and into the future. This flow of time is fundamental to how we understand our universe and how we think about the passage of events. But with time crystals, this linear progression seems to be turned on its head. Instead of following the usual pattern of moving from one state to another, time crystals exhibit a kind of cyclical motion that redefines what it means for something to be in motion over time. The most exciting aspect of this discovery is that time crystals could potentially lead to new technologies that allow us to manipulate the flow of time itself. Quantum computers rely on the principles of quantum mechanics to perform calculations much faster than traditional computers. Time crystals, with their ability to maintain a periodic motion, could potentially help stabilize quantum systems, making them more reliable and durable. One of the major challenges in the development of quantum computers is that the qubits used in quantum systems are highly sensitive to their environment, which causes them to lose their quantum state and behave unpredictably. This is known as quantum decoherence, and it limits the practical use of quantum computers. Time crystals could help mitigate this issue by providing a stable, self-sustaining form of motion within quantum systems. This stability could potentially make quantum computers more robust, allowing them to perform longer and more complex computations without the risk of losing their state. Because they do not lose energy during their oscillations, time crystals also present the possibility of creating systems that store and use energy more efficiently. In traditional systems, energy is often lost as heat or through other forms of dissipation. But in the case of time crystals, their motion is sustained without the need for external energy input, which could lead to the development of energy-efficient systems that could drastically reduce energy waste. While we are still a long way from practical applications, the concept of using time crystals to create perpetual motion or ultra-efficient energy systems remains a tantalizing possibility. For centuries, physicists have understood the behavior of matter and energy through the lens of thermodynamics, particularly the second law of thermodynamics. Time crystals seem to violate this principle. This does not mean that time crystals are impossible or that the laws of physics are being broken, but rather that our understanding of thermodynamics and the flow of time may need to be revised. Time crystals offer a glimpse into the strange and unpredictable nature of quantum mechanics, where things can behave in ways that are difficult to reconcile with our everyday experiences. Quantum entanglement, a glimpse into faster-than-light communication. Quantum entanglement is one of the most mind-bending phenomena in the world of quantum mechanics. It's a concept so strange it seems unreal. Two particles can be connected in such a way that the state of one particle instantly affects the state of the other, no matter how far apart they are. At its core, quantum entanglement refers to a phenomenon in which two or more particles become intertwined in such a way that their properties, such as their spin, position, or polarization, are linked. Once entangled, changing the state of one particle will immediately change the state of the other, even if the particles are light years apart. This spooky action at a distance, as Albert Einstein famously called it, defies classical understanding, where information and effects are assumed to travel only at the speed of light or slower. To visualize this, think of two particles, say electrons, that have interacted in such a way that they become entangled. Now, if you measure the spin of one of the electrons, its entangled partner, no matter where it is, will instantly take on the opposite spin. If one electron is on Earth and the other is on a distant star, measuring the spin of the Earth-bound electron will instantaneously determine the spin of the faraway electron with no delay. This connection seems to happen outside of the time and space constraints that govern our everyday experience. In the quantum world, particles don't have definite positions or speeds until they're measured. Instead, they exist in a superposition, meaning they can be in multiple states at once. When two particles become entangled, their states become linked in a way that is independent of the space separating them. This is sometimes described as a quantum handshake. For many years, quantum entanglement was considered a theoretical oddity, something that could be described mathematically but couldn't be practically observed. However, in recent decades, experimental advancements have demonstrated the reality of quantum entanglement. Scientists have entangled pairs of photons, electrons, and even atoms, and observed the strange behaviors predicted by quantum mechanics. These experiments have confirmed that entanglement is real, though the exact nature of how the particles communicate across space remains a profound mystery. If entangled particles can affect one another instantly, could this provide a way to send information at speeds faster than light? In theory, it might seem possible. If you could entangle two particles, send them in opposite directions, and then manipulate one of the particles, you might be able to instantaneously transmit information to the other particle, no matter how far apart they are. Faster-than-light communication is a tantalizing concept, but it runs into several fundamental challenges. For one, the process of measuring one of the entangled particles doesn't allow for the transfer of any useful information on its own. In quantum mechanics, the act of measurement forces the particle into a specific state, but the outcome of the measurement is random. So, while the state of the second entangled particle is determined by the first, the result is not something that can be controlled or predicted. This means that entanglement alone does not provide a reliable means of sending information. Moreover, entanglement cannot be used to send a message faster than the speed of light without violating the principle of causality, which is the foundation of relativity. According to Einstein's theory of relativity, information can't travel faster than the speed of light, because it would imply the possibility of information traveling backward in time, leading to paradoxes. If quantum entanglement allowed for faster-than-light communication, it could lead to scenarios where events could be observed in reverse order, which would have profound implications for our understanding of time and causality. In spite of these challenges, researchers are still exploring ways in which quantum entanglement could be harnessed for communication. One of the most promising areas of research is quantum teleportation, a technique that uses entanglement to transmit quantum information from one place to another. While it doesn't involve the transmission of matter itself, quantum teleportation allows for the state of a quantum system to be transferred to a distant location, using entanglement to ensure that the two systems are linked. This process, which has been demonstrated in laboratory settings, could potentially be applied to more practical forms of communication in the future. Quantum entanglement also plays a key role in the development of quantum networks. Just as classical computers use networks of connected devices to share information, quantum computers could one day form a global quantum internet. This quantum internet would rely on the principles of entanglement and quantum teleportation to send quantum data between devices. Instead of using traditional binary bits, which are either 0 or 1, quantum computers would use quantum bits or qubits, which can exist in superpositions of states. This could allow for far more efficient and secure communication. While faster-than-light communication remains an elusive dream, the exploration of entanglement has had many real-world applications. Quantum entanglement has important implications for fields such as cryptography, computing, and even fundamental physics. The phenomenon of entanglement has already been used in experiments to develop ultra-secure communication methods, known as quantum cryptography. In this technique, entangled particles are used to encrypt information in a way that makes it virtually impossible to intercept without altering the data. This has the potential to revolutionize secure communication, making it far more difficult for hackers or eavesdroppers to access sensitive information. Entanglement is also crucial to the development of quantum computers. As mentioned earlier, quantum computers harness the principles of quantum mechanics to perform computations far faster than classical computers. The power of quantum computing comes from the ability to process large amounts of data in parallel, thanks to the superposition and entanglement of qubits. Quantum entanglement enables quantum computers to solve certain types of problems that would be infeasible for classical computers, such as simulating complex molecular structures or optimizing large systems. Scientists are still grappling with the fundamental nature of entanglement and how it might be harnessed for practical use. One of the central questions is whether entanglement can be made more reliable and less susceptible to error. In the quantum world, systems are inherently fragile and can be easily disrupted by their environment. Finding ways to stabilize entangled particles and prevent them from losing their quantum coherence is a major challenge in the field. What does it mean for two particles to be connected across vast distances, instantly sharing information? Does this suggest that space and time are not as separate as we once thought, and that there is some deeper connection between all parts of the universe? Some have suggested that entanglement could be a clue to the existence of a deeper, more fundamental layer of reality that transcends our classical understanding of space and time. Why are some exoplanets denser than iron? Exoplanets have revealed a staggering diversity in size, composition, and behavior, challenging our understanding of how planets form and evolve. Among the most puzzling discoveries are ultra-dense exoplanets, worlds so heavy for their size that they defy conventional explanations. Some of these planets have densities higher than iron, raising questions about their structure and the processes that created them. A planet's density tells us a lot about its composition. A planet like Earth, with an average density of about 5.5 grams per cubic centimeter, has a mix of rocky material and metals, with a dense iron-nickel core at its center. Gas giants like Jupiter and Saturn have much lower densities because they are made mostly of hydrogen and helium. But some exoplanets stand out because their densities are extreme, far beyond what we see in the solar system. These planets are often smaller than Earth, but significantly heavier, suggesting they are composed almost entirely of metal or other unknown materials. One such example is the exoplanet K2 229b, located about 335 light-years away. It is slightly smaller than Earth, but has a mass nearly 2.6 times greater, giving it an average density of around 8.9 grams per cubic centimeter, similar to pure iron. Another example is Kepler 107c, a planet with a density of approximately 12.6 grams per cubic centimeter. These numbers suggest that these planets are predominantly metallic, with very little silicate rock or other lighter materials. How such planets form and what they reveal about planetary systems are questions that have sparked intense research. The first step in understanding ultra-dense exoplanets is determining whether their observed properties could be explained by extreme conditions during their formation. One possibility is that these planets are the remnants of larger worlds that underwent catastrophic events, such as giant impacts. In this scenario, a collision with another massive body could strip away the planet's outer layers, leaving behind a dense metallic core. This is similar to what scientists believe happened to Mercury, which has a disproportionately large iron core compared to its size. However, the planets in question are even denser than Mercury, suggesting that they may have experienced even more dramatic events. Many of these dense exoplanets orbit extremely close to their stars, sometimes completing an orbit in just a few hours or days. This close proximity exposes them to intense radiation and tidal forces, which could strip away their lighter outer layers over time. This process, known as photoevaporation, is thought to be common for planets near their stars, particularly smaller ones. If a planet starts out as a larger body with a thick atmosphere or a silicate-rich crust, the intense heat and radiation could gradually remove these layers, leaving behind a dense metallic core. Yet, even these scenarios don't fully explain the extreme densities observed in some exoplanets. Kepler 107c shares its system with another planet, Kepler 107b, which is similar in size but much less dense. Both planets orbit the same star, which raises questions about why one would lose so much of its mass while the other remains relatively intact. This suggests that there may be additional factors at play, such as differences in composition or the timing of formation events. One hypothesis that has gained attention is that ultra-dense exoplanets might have formed in regions of their planetary systems where metallic materials were unusually abundant. In the early stages of a planetary system's formation, dust and gas orbiting the young star begin to coalesce into planets. The composition of this material depends on its distance from the star, with rocky and metallic elements dominating closer in and lighter, volatile materials like water and gases accumulating farther out. If a protoplanetary disk contained regions with a higher concentration of metals, it's possible that some planets could form with an unusually high metallic content right from the start. Another possibility is that these planets formed as the metallic cores of gas giants. In this scenario, a gas giant loses its thick atmosphere, either through tidal stripping by its host star or during a violent interaction with another planet or star. What remains is the dense core, which would explain the high density observed. This idea aligns with the discovery of super-Earths and mini-Neptunes in close orbits around stars, planets that may represent a continuum between rocky worlds and stripped gas giants. Planets with such high densities are unlikely to support life as we know it, as their compositions suggest they lack significant atmospheres or water. However, studying these planets can help refine our models of planetary evolution, improving our ability to identify planets that might be more suitable for life. For instance, understanding how close-in planets lose their atmospheres could help scientists estimate the conditions under which Earth-like planets could retain theirs, even in harsh environments. Instruments such as the Transiting Exoplanet Survey Satellite, or TESS, and the James Webb Space Telescope, or JWST, are providing more detailed data about these mysterious worlds. By analyzing their light curves, spectra, and gravitational interactions with nearby planets, scientists can gain insights into their compositions, orbits, and formation histories. Just as the discovery of hot Jupiters challenged traditional models of planetary formation, the study of ultra-dense exoplanets could reveal previously unimagined possibilities. Some scientists have speculated about the existence of planets made largely of exotic materials, such as carbon or diamond, formed under extreme pressures and temperatures. The discovery of ultra-dense exoplanets suggests that the universe is far more diverse and surprising than we ever imagined. Is the universe conscious? A new perspective on panpsychism. For centuries, humans have debated the nature of consciousness, attempting to understand how it arises and whether it is unique to living beings. Most of modern science focuses on the brain as the seat of consciousness, tying it to complex networks of neurons and the intricate processing of information. However, an ancient and enduring philosophical perspective, known as panpsychism, suggests that consciousness might not be limited to living beings. Instead, it could be a fundamental property of the universe itself, woven into the very fabric of reality. Panpsychism is not a new idea. Philosophers like Plato and Aristotle considered the possibility that everything in existence possesses some degree of consciousness, no matter how small. In the 17th century, the philosopher Gottfried Leibniz introduced the concept of monads, indivisible units of reality that each contained a form of consciousness. In more recent times, thinkers like Alfred Whitehead and Galen Strawson have revisited the idea, presenting panpsychism as a serious contender in the debate over the nature of consciousness. The modern revival of panpsychism arises from a fundamental problem in science: the hard problem of consciousness. While researchers have made great strides in understanding how the brain works, they have struggled to explain why subjective experiences, what it feels like to be aware, exist at all. This challenge, first articulated by philosopher David Chalmers, highlights the gap between objective descriptions of brain activity and the subjective experience of being. Panpsychism offers a potential solution by suggesting that consciousness doesn't emerge from complex systems like brains, but is instead a basic aspect of reality, present even in the simplest forms of matter. If consciousness is fundamental, it might exist at the level of subatomic particles, like electrons and quarks. In this view, these particles would not have thoughts or feelings as we understand them, but would possess a rudimentary form of awareness. This tiny spark of consciousness, when combined in vast numbers and organized in complex ways, could give rise to the rich inner experiences we associate with human and animal minds. In this way, panpsychism provides a framework for bridging the gap between the material world and the subjective realm of experience. Rather than viewing the cosmos as a collection of lifeless particles governed by impersonal laws, it invites us to consider the possibility that the universe has an inner dimension, a kind of awareness that permeates everything. Could the universe itself have a kind of consciousness, shaped by the interactions of countless smaller conscious entities? And if so, what might this cosmic awareness look like? Critics of panpsychism often argue that it is unfalsifiable, that is, it cannot be tested or proven through scientific methods. While this is a valid concern, some researchers are exploring ways to investigate the idea indirectly. For instance, neuroscientists and physicists are examining whether certain mathematical frameworks, like integrated information theory, or IIT, could provide insights into how consciousness might emerge from physical systems. IIT proposes that consciousness arises from the way information is processed and integrated within a system. If this theory holds true, it could support the idea that even simple systems, like atoms or molecules, possess a minimal form of consciousness. Another avenue of exploration involves the study of complex systems, such as ecosystems or galaxies. These systems exhibit emergent behaviors, patterns and properties that arise from the interactions of their parts. Some researchers speculate that consciousness could be an emergent property of the universe as a whole, arising from the intricate interplay of matter and energy on a cosmic scale. Some interpretations of panpsychism suggest that the universe's awareness might be diffuse and fragmented, with no overarching intelligence or intention. Others propose that the universe could have a form of self-awareness, shaped by the collective interactions of its parts. While these ideas remain speculative, they offer a fascinating lens through which to explore the mysteries of existence. If the universe is aware, even in a limited sense, it could reshape our understanding of existence and our relationship with the cosmos. It might also challenge our assumptions about life and intelligence, suggesting that these qualities are not unique to biological organisms, but are instead manifestations of a deeper, universal property. This perspective could inspire new approaches to questions about the origin of life, the search for extraterrestrial intelligence, and the nature of reality itself. Do fundamental physical constants change over time? The fundamental physical constants, like the speed of light, the gravitational constant, and the fine structure constant, serve as the unchanging foundation of the physical laws that govern everything. They define the strength of forces, the behavior of particles, and even the structure of space and time. But the idea that these constants are truly immutable has been questioned over the years, with some scientists exploring whether they might change over time or vary across different regions of the universe. The speed of light, denoted as c, is one of the most iconic constants in physics. It is the ultimate speed limit of the universe, dictating how fast information and matter can travel. In Einstein's theory of relativity, c is central to the equations that link space and time. Yet some researchers have proposed that this value might not have always been the same. Theories that suggest a varying speed of light often arise in attempts to explain certain puzzles in cosmology, like the horizon problem. This problem involves the question of how distant regions of the universe appear to have the same temperature, even though they should not have been able to exchange information or energy due to the constraints of the speed of light. If the speed of light was faster in the early universe, it could provide an explanation for this apparent uniformity. Such an idea is speculative, but not without merit. Scientists have examined ancient light, like that from the CMB, to look for evidence of changes in C. While no definitive proof has been found, the search continues, as even a tiny variation could have profound implications for our understanding of the cosmos. The gravitational constant, g, governs the strength of gravity, the force that shapes the large-scale structure of the universe. If g were different in the past, it could have affected the formation of stars, galaxies, and planetary systems. Observations of ancient celestial objects, like distant stars and quasars, offer a window into the universe's past. By studying how these objects behave, scientists can infer whether the value of g has remained stable over billions of years. So far, the evidence suggests that g has not changed significantly, but the possibility of subtle variations cannot be ruled out entirely. The fine structure constant, often represented by the symbol alpha, is another key player in this discussion. It describes the strength of the electromagnetic force, which governs interactions between charged particles. Unlike c or g, alpha is a dimensionless constant, meaning it has no units and is simply a number that encapsulates the ratio of several fundamental quantities. This makes it particularly intriguing to physicists because it appears to be a pure, universal value. However, some studies have suggested that alpha might vary over time or space. One of the most compelling pieces of evidence for a varying alpha comes from observations of distant quasars. Light from these incredibly bright objects passes through interstellar gas clouds on its way to Earth, creating absorption lines in the light spectrum. By analyzing these lines, scientists can measure the value of alpha at different points in the universe's history. Some studies have reported tiny shifts in alpha over billions of years. However, these results are controversial and have not been universally accepted, as they rely on extremely precise measurements that are difficult to verify. The implications of changing constants are enormous. If these values vary, it would mean that the laws of physics themselves are not fixed, but evolve over time or differ across regions of the universe. This challenges the principle of universality, a cornerstone of modern science. It could also open the door to new physics, revealing deeper layers of reality that we have yet to uncover. In string theory and related frameworks, the universe is thought to have more dimensions than the 3 of space and 1 of time that we experience. These extra dimensions could influence the values of physical constants, causing them to change over time as the universe evolves. For instance, the shape or size of these dimensions might shift, altering the constants in subtle ways. If the constants were even slightly different, stars might not form, atoms might not hold together, and life as we know it would be impossible. This raises the question of whether our universe is just one of many in a multiverse, each with its own set of constants. In such a scenario, the constants in our universe might appear to vary because we are observing only a small part of a much larger reality. Observatories and laboratories around the world are pushing the limits of precision to measure these values over time and across different environments. Atomic clocks, which rely on the frequencies of electromagnetic radiation emitted by atoms, are being used to detect potential variations in alpha. These clocks are so accurate that even the tiniest shift in the fine structure constant could be detected over long periods. By studying distant galaxies, stars, and other cosmic phenomena, astronomers can gather data on how the universe's fundamental properties have changed or stayed the same over billions of years. The results of all these different studies will either reinforce our current understanding of physics or point us towards new and exciting discoveries. The shadow biosphere. Could entire ecosystems be invisible to us? The idea of a shadow biosphere is that there could be life forms on Earth that exist right alongside us, but are so different from what we recognize as life that they remain undetected. These organisms would operate on an entirely different set of biochemical rules, possibly using molecules and processes unfamiliar to biology as we know it. Life is based on a few key ingredients: carbon as a building block, water as a solvent, and DNA or RNA as carriers of genetic information. These commonalities form the basis of what scientists call standard biochemistry. But the shadow biosphere hypothesis proposes that life could exist outside these rules. It might use alternative elements like silicon instead of carbon, or solvents like methane instead of water. Such life forms could even rely on completely different molecules for storing and transmitting genetic information. Earth's environments are incredibly diverse. From boiling hydrothermal vents at the bottom of the ocean to freezing, oxygen-deprived lakes beneath Antarctic ice, life has proven its ability to thrive in extreme conditions. The discovery of extremophiles, organisms that live in these harsh environments, has already expanded our understanding of where life can exist. But what if these environments also host life forms that are so fundamentally different that our tools and methods can't detect them? Current techniques for identifying microorganisms rely heavily on standard assumptions. For example, scientists often look for DNA, RNA, or proteins when searching for life. If an organism doesn't use these molecules, it might not show up in our analyses. Similarly, we tend to culture microbes in lab conditions that mimic environments we think they prefer. But if an organism thrives in vastly different conditions, it might never grow in our petri dishes, leaving its existence unnoticed. One possibility is that a shadow biosphere might consist of organisms that rely on arsenic instead of phosphorus. Phosphorus is a key component of DNA, RNA, and ATP, the molecule that provides energy for cellular processes. However, arsenic, which is chemically similar to phosphorus, is toxic to most known life forms because it disrupts these processes. In 2010, a controversial study claimed to have discovered a bacterium in California's Mono Lake that could substitute arsenic for phosphorus in its DNA. Although this finding was later disputed, it highlighted the possibility that life could exist with alternative chemistries. Silicon is abundant on Earth and shares some chemical properties with carbon, making it a candidate for supporting life. Some scientists argue that it could be plausible under the right conditions. For instance, in environments with little oxygen but abundant silicon compounds, life forms might evolve to build their structures and processes around silicon instead of carbon. The shadow biosphere might also be hiding in plain sight within our own cells. Some researchers speculate that organelles, such as mitochondria, could have evolved from ancient shadow life forms that became integrated into standard biochemistry. If this is true, remnants of alternative life chemistries might still be present, hidden deep within the cellular machinery of modern organisms. If alternative biochemistries exist on Earth, they could provide clues about what to look for on other planets and moons. The methane lakes on Saturn's moon Titan, or the subsurface oceans of Jupiter's moon Europa, might host life forms that don't rely on water or carbon. By studying the potential for shadow life on Earth, we could better prepare to recognize life in alien environments. If shadow life exists, it could be interacting with us in ways we don't understand. These organisms might be harmless, or they could play roles in diseases or environmental processes that we currently attribute to other causes. Identifying and studying them could open new avenues for treating illnesses or managing ecosystems. Searching for a shadow biosphere is incredibly challenging. It requires developing new tools and methods that don't rely on the assumptions of standard biochemistry. Scientists need to design experiments that are open-ended enough to detect unfamiliar chemistries while avoiding false positives from known organisms. This involves rethinking everything from how we sample environments to how we analyze the results. Some efforts are already underway. Researchers are exploring extreme environments on Earth, such as deep-sea hydrothermal vents, highly acidic lakes, and salt flats, in the hopes of finding hints of alternative life. These locations are thought to mimic conditions that might have existed on early Earth or on other planets, making them prime candidates for hosting shadow ecosystems. Advanced imaging techniques and molecular analyses are also being developed to identify structures or processes that don't match known biological patterns. If such life exists, it would mean that Earth has hosted multiple origins of life. It would suggest that life is not a rare accident, but a natural outcome of the right conditions, even if those conditions differ dramatically from what we consider normal. This, in turn, could have profound implications for the search for life beyond Earth, implying that the universe might be teeming with diverse forms of life. Skeptics argue that the lack of evidence for shadow life suggests it doesn't exist, but proponents counter that the absence of evidence is not evidence of absence, especially when our tools are not designed to find what we're looking for. The history of science is filled with discoveries that were missed for decades or centuries, simply because no one knew how to look for them. Cosmic panspermia. Did life on Earth originate in the stars? At the heart of panspermia is the idea that the ingredients for life can travel through space. Comets, asteroids, and interstellar dust are the primary suspects for carrying these materials. These celestial objects are rich in carbon-based compounds, the essential ingredients for organic chemistry. For example, comets are known to contain water ice, carbon dioxide, and a variety of organic molecules. When these objects collide with planets, they can deliver these materials to planetary surfaces, creating conditions where life might emerge. The hypothesis gains support from discoveries of complex organic molecules in space. Observations with telescopes and space probes have revealed that amino acids, the building blocks of proteins, exist in the interstellar medium. These molecules form in the cold, dense regions of space, where dust and gas clouds provide the right conditions for chemical reactions. Some of these molecules become embedded in comets and asteroids, preserved in their icy interiors as they travel through the cosmos. When these objects impact a planet, the heat and energy from the collision could trigger further chemical reactions, potentially leading to the formation of more complex compounds like RNA or DNA. Earth's early history provides a potential stage for panspermia to play out. Over 4 billion years ago, our planet experienced a period known as the Late Heavy Bombardment, during which it was pummeled by a constant barrage of comets and asteroids. These impacts likely delivered vast amounts of water and organic material to the Earth's surface. Some scientists argue that this influx of materials could have jump-started the process of life, providing the raw ingredients in an environment conducive to their assembly into living systems. One compelling piece of evidence comes from the study of meteorites. Some meteorites that have fallen to Earth contain amino acids and other organic molecules. The Murchison meteorite, which landed in Australia in 1969, is a famous example. It contains around 70 different amino acids, many of which are not found naturally on Earth. The presence of these molecules suggests that the basic components of life can form in space and survive the journey through our atmosphere. Experiments have also shown that certain bacteria and other microorganisms can endure extreme environments, such as intense radiation, vacuum, and freezing temperatures. For instance, tardigrades, tiny, resilient creatures often called water bears, have been shown to survive in space. These findings raise the possibility that simple life forms could hitch a ride on comets, asteroids, or even spacecraft, spreading from one planet to another. Some take the idea further, suggesting that life itself might have originated elsewhere and traveled to Earth fully formed. This version of panspermia, called directed panspermia, proposes that intelligent civilizations could have intentionally seeded life on other planets. While this idea lacks direct evidence, it opens up fascinating questions about the origins of life and our place in the universe. If life's building blocks are widespread in the universe, it increases the likelihood that life exists elsewhere. Planets and moons within our solar system, such as Mars, Europa, and Enceladus, are prime targets for exploration because they may have received similar materials to those delivered to Earth. Mars, in particular, shows evidence of past liquid water and has organic molecules in its soil, making it a candidate for panspermia-driven life. Many exoplanets lie within the habitable zones of their stars, where conditions might allow liquid water to exist. If comets and asteroids delivered organic materials to these planets as they did to Earth, it's possible that similar processes could lead to the emergence of life. Moreover, the detection of interstellar objects like Oumuamua and 2I/Borisov has now confirmed that material from other star systems can travel across the galaxy, potentially spreading the seeds of life far and wide. Critics of panspermia argue that while it explains how life's ingredients might spread, it doesn't solve the deeper question of how life originated in the first place. Whether life began in the depths of space or on a young Earth, the transition from non-living molecules to living systems remains one of the biggest mysteries in science. Panspermia shifts the focus of this question but doesn't eliminate it. Missions like the European Space Agency's Rosetta probe, which studied the comet 67P/Churyumov-Gerasimenko, have provided valuable insights into the composition of comets and their potential to deliver organic materials. Future missions, such as sample return missions from asteroids, comets, moons, and planets, will likely shed more light on the role panspermia may have played in the cosmic distribution of life's building blocks. Dark fluid, a unified explanation for dark matter and dark energy. Together, dark matter and dark energy account for about 95% of the universe's total mass energy content, yet they remain elusive and largely undefined. They are often treated as separate phenomena, but the concept of dark fluid challenges this view. It suggests that these two forces might be manifestations of a single, unified entity, a fluid-like substance pervading the cosmos. Dark matter's influence is most apparent on galactic and intergalactic scales, where its gravitational effects prevent galaxies from flying apart. Dark energy, on the other hand, becomes dominant on the largest scales, pushing galaxies away from each other and accelerating the universe's expansion. This duality has led some scientists to propose that these phenomena might not be separate at all, but rather different aspects of the same underlying force. Dark fluid theory proposes that the universe is filled with a single substance that behaves differently depending on the context. On smaller scales, this fluid might cluster and act like dark matter, creating the gravitational pull needed to form and stabilize galaxies. On larger scales, it could spread out and exert a repulsive force, driving the accelerated expansion of the universe like dark energy. This approach aims to simplify our understanding of the cosmos by unifying two of its greatest mysteries into one. One way to think about dark fluid is to imagine it as a substance with variable density and pressure. In regions where the density is high, its gravitational effects dominate, mimicking the behavior of dark matter. In regions where the density is low, its repulsive effects become more apparent, resembling dark energy. Mathematically, the dark fluid hypothesis builds on modifications to general relativity and the equations that describe the behavior of matter and energy in the universe. Some models propose that dark fluid has a negative pressure, a property that allows it to drive cosmic acceleration. Others suggest that its behavior changes over time, transitioning from dark matter-like effects in the early universe to dark energy-like effects in the present era. Observational evidence supporting the dark fluid idea is indirect but compelling. One clue comes from the large-scale structure of the universe, which shows a web-like distribution of galaxies and dark matter. Simulations suggest that this structure could arise naturally from a single fluid-like substance with the right properties. Additionally, measurements of the CMB reveal patterns that could be consistent with a dark fluid model. Some theories propose that dark fluid could be a manifestation of quantum fields that permeate the universe. These fields might have unusual properties, such as negative energy density or exotic forms of interaction, that give rise to the observed effects of dark matter and dark energy. If true, this connection could also bridge the gap between cosmology and quantum mechanics. In standard physics, gravity is described as the curvature of space-time caused by mass and energy. However, if dark fluid exists, it might require a new understanding of gravity that goes beyond Einstein's theory of general relativity. Alternative theories of gravity, such as MOND or emergent gravity, could be compatible with the idea of dark fluid. These theories suggest that gravity behaves differently on large scales or in the presence of certain substances, potentially providing a framework for dark fluid. Critics of the dark fluid hypothesis point out that while the idea is mathematically elegant, it has yet to make specific predictions that can be tested through observations or experiments. Additionally, some argue that the separate theories of dark matter and dark energy, while incomplete, are already supported by a wealth of data and do not necessarily need to be unified. Despite these challenges, the dark fluid concept represents a bold attempt to simplify our understanding of the universe. Astronomers and physicists are using advanced telescopes and simulations to study the behavior of galaxies, galaxy clusters, and the cosmic web. They are also analyzing data from missions like the Planck satellite, which has provided detailed measurements of the CMB. Some researchers are investigating the properties of exotic materials and quantum fields that might mimic the behavior of dark fluid. Others are designing experiments to test alternative theories of gravity or search for new particles that could be related to dark matter and dark energy. Type 3 civilizations. What would a galaxy-spanning society look like? The Kardashev scale, developed in 1964 by astrophysicist Nikolai Kardashev, is a method to measure a civilization's technological advancement based on its energy consumption. A Type 3 civilization is one capable of harnessing and utilizing the energy output of an entire galaxy. This level of development would place such a society far beyond anything humanity can currently grasp, involving the use of resources on a scale that stretches across billions of stars and planets. At this level, the galaxy itself becomes the civilization's domain. They would not just inhabit a single star system, but expand to countless systems, creating interconnected networks that span light years. This scale of expansion would require technology capable of overcoming the vast distances of space. The civilization would likely have developed faster-than-light travel or wormhole-based transportation, enabling them to move people, materials, and information quickly and efficiently across the galaxy. Without such methods, even the nearest stars would take thousands of years to reach using conventional propulsion systems. One of the first questions is how such a civilization might manage energy on a galactic scale. Harnessing the power of stars would be central to their capabilities. They might construct Dyson spheres or swarms around individual stars, capturing the vast energy output and directing it for their use. If this were done on a galactic scale, the civilization would have access to an almost unimaginable amount of energy. Beyond stars, a Type 3 civilization would likely extract energy from the rotational momentum of a spinning black hole through a process called the Penrose mechanism. This involves sending matter close to the black hole's event horizon, where it splits into two parts, one falling into the black hole and the other escaping with more energy than it originally had. Advanced civilizations might also exploit the intense radiation from accretion disks or even manipulate the mysterious forces associated with dark energy and dark matter. Planet-sized constructs, artificial habitats, and space stations could dot the galaxy, serving as hubs for activity. They might transform entire planets into machines or computational nodes, known as matryoshka brains, capable of performing unimaginable amounts of processing. These structures could coordinate the vast operations required to manage a galaxy-wide society, from energy collection to interstellar trade and communication. They might no longer exist as biological entities, having transitioned into digital or post-biological forms. Their consciousness could be stored and shared across vast networks, allowing individuals to inhabit multiple bodies or even live entirely in virtual realities. This would free them from many of the limitations of biological life, such as the need for food, water, or specific environmental conditions. They could have the ability to engineer entire star systems, moving planets and stars to optimize energy use or create ideal living conditions. Stellar engines, massive structures designed to move stars, might be employed to reshape the galaxy's layout. They could even manipulate the life cycle of stars, extending their lifespans or triggering supernova to harvest their energy. These actions would leave clear signatures, and some astronomers have suggested that searching for such anomalies could help us detect advanced civilizations. The distances between stars are so vast that even light takes years to travel from one system to another. To overcome this, they might use advanced quantum communication, relying on phenomena like quantum entanglement to send information instantaneously. Alternatively, they could use wormholes or other hypothetical constructs to bridge the distances. These methods would allow them to maintain cohesion across their sprawling society, ensuring that knowledge and decisions could flow seamlessly. Such a society would likely be highly cooperative, as the challenges of managing a galaxy's resources would require collective effort. Alternatively, they could be fragmented, with different factions or species controlling various parts of the galaxy. The dynamics of such a civilization would depend on their values, history, and level of technological integration. They could be explorers, seeking to understand and catalog every form of life in the galaxy, or they might be creators, seeding new worlds with life to study its development. On the other hand, they might view less advanced civilizations as irrelevant or even dangerous, avoiding contact to prevent contamination or conflict. This perspective aligns with ideas like the zoo hypothesis. Their activities would likely leave observable traces, such as unusual patterns of light from stars surrounded by Dyson spheres, or unexplained energy emissions from black holes. Some researchers have proposed searching for these techno-signatures as part of the search for extraterrestrial intelligence. However, the sheer scale of the universe and the limits of our current technology make this an incredibly challenging endeavor. Von Neumann probes. Could self-replicating machines already be among us? Proposed by the mathematician and physicist John von Neumann probes are theoretical devices designed to explore space autonomously. Unlike traditional spacecraft, which require a continuous supply of materials and human oversight, von Neumann probes would have the capability to replicate themselves using the raw materials they encounter on planets, moons, or asteroids. This ability would allow them to multiply and spread exponentially, covering vast distances and potentially exploring the entire galaxy. A civilization capable of creating such machines would not need to launch millions of spacecraft from their home planet. Instead, they could send out a few probes to begin the process, letting replication handle the rest. These probes could be equipped with advanced sensors, communication systems, and tools for resource extraction and manufacturing. Once launched, they would seek out suitable materials to construct copies of themselves, continuing the cycle as they venture further into the galaxy. If an advanced alien civilization has created von Neumann probes, they might already be in our solar system. The probes could be programmed to observe, study, and collect data discreetly, avoiding detection by local intelligent life forms. A von Neumann probe could be designed to remain hidden, blending into its surroundings, or operating in regions where human technology has limited reach, such as the outer solar system. Perhaps these probes could take advantage of small, inconspicuous celestial bodies, such as asteroids or comets. These objects provide a wealth of raw materials that could be used for replication, as well as a natural camouflage against the backdrop of space. Probes could hollow out an asteroid, creating an internal factory to produce new machines while appearing as just another rock in the vast expanse of space. This would make them incredibly difficult to detect with our current technology. Instead of sending constant signals that could be intercepted, they might use bursts of data at irregular intervals or employ quantum communication methods that leave no detectable trail. Alternatively, they might not communicate at all until a predefined goal is achieved, such as reaching a specific number of probes or exploring a particular region of the galaxy. Von Neumann probes raise certain implications for the search for extraterrestrial intelligence. While traditional efforts like SETI focus on detecting radio signals from distant civilizations, the search for von Neumann probes would require a different approach. It might involve looking for anomalies in the behavior of asteroids, unexplained patterns in space debris, or technological signatures that don't match natural processes. These probes, being autonomous, could exhibit behaviors that seem out of place, such as sudden changes in trajectory or unusual thermal emissions. Earth's geological history offers plenty of opportunities for probes to monitor the planet. They might have arrived when Earth was a young, lifeless world, or they could have come later to observe the rise of life and civilization. These probes could be hidden beneath the surface of the Moon, buried on Mars, or even stationed in stable regions like the Lagrange points, where gravitational forces create areas of relative stability. While most UAP sightings are likely to have conventional explanations, the idea that some might represent alien technology, while unlikely, cannot be entirely dismissed. Von Neumann probes, with their advanced capabilities, could potentially operate in Earth's atmosphere to gather data, appearing as fleeting, mysterious objects before vanishing again. If humanity were to discover a von Neumann probe, it would be one of the most profound events in history. The presence of such a device would confirm not only the existence of extraterrestrial intelligence, but also their ability to engineer machines far beyond our current capabilities. Understanding the probe's purpose would be a priority. Is it here to observe, to communicate, or to prepare for something else? The answers could provide valuable insights into the intentions and nature of the civilization that created it. Building von Neumann probes is not an entirely distant concept for humans either. Advances in robotics, artificial intelligence, and 3D printing are laying the groundwork for self-replicating machines. The challenges are still immense, particularly in creating systems that can operate autonomously for extended periods and adapt to unforeseen circumstances. However, the potential benefits of such technology are equally vast, from enabling humanity to explore the galaxy to ensuring the survival of our species by spreading life to other worlds. If not carefully created, such machines could potentially spiral out of control, consuming resources indiscriminately and disrupting natural systems. This scenario, sometimes referred to as the grey goo problem, highlights the need for safeguards to prevent unintended consequences. Advanced civilizations that build von Neumann probes would likely have faced similar challenges, refining their designs to avoid such pitfalls. Are Dyson swarms more likely than Dyson spheres? First proposed by physicist and mathematician Freeman Dyson, The Dyson sphere involves a massive structure surrounding a star to capture its energy output. The sheer scale of such a project is almost incomprehensible, requiring materials and engineering capabilities far beyond anything humanity currently possesses. However, an alternative concept, the Dyson swarm, may be more feasible. Instead of a single solid megastructure, a Dyson swarm envisions a vast collection of individual solar collectors orbiting a star, each gathering energy and transmitting it back to a central hub or directly to planets and stations in the system. Constructing a single sphere around a star would require a mind-boggling amount of material, precision engineering, and coordination. A swarm, on the other hand, can be built incrementally. Small solar collectors could be launched into orbit around a star one at a time, gradually expanding the swarm over decades or centuries. This approach allows for continuous energy harvesting during construction, making it an attractive option for civilizations that might need to expand their energy capabilities gradually. A solid sphere surrounding a star would face incredible stresses from gravitational forces, radiation pressure, and thermal expansion. These stresses would require advanced materials that might not even exist. A swarm of independent units, however, wouldn't need to support its own weight or withstand these forces as a single structure. Each collector operates independently, orbiting the star in a carefully coordinated pattern to avoid collisions. The collectors might be simple solar panels, optimized to capture as much energy as possible. Alternatively, they could be more advanced devices, capable of focusing light, storing energy, or even performing computations directly within the swarm. Some concepts even suggest that the collectors could double as habitats, providing living space for billions of individuals. This dual-purpose design would maximize the utility of the swarm, making it not just an energy harvesting system, but a thriving extension of a civilization. The energy collected by a Dyson swarm could be transmitted in various ways. One possibility is to use microwave or laser beams to send energy to receiving stations on planets, moons, or spacecraft. This method would require precise targeting systems and safeguards to prevent the energy beams from causing damage. Another option is to use a system of energy relays, where the collectors transmit power to nearby units, creating a network that delivers energy wherever it's needed. The efficiency of these methods would depend on the distance and technology involved, but the basic principle is straightforward. A solid Dyson sphere would require more matter than exists in many planetary systems, making it an almost impossible task. A swarm, however, could be constructed using materials from asteroids, moons, or even the outer layers of gas giants. A civilization could mine metals and silicates from asteroid belts, process them into solar collectors, and launch them into orbit around their star. The resources of an entire solar system might still be needed, but the demands would be spread out over time, making the project more manageable. A solid sphere would block all light from the star it surrounds, plunging any planets in the system into darkness and drastically altering their climates. A swarm, on the other hand, can be designed to allow light to pass through in a controlled way. The orbits of the collectors can be arranged to ensure that planets still receive sunlight, preserving their ecosystems and habitability. This flexibility makes a swarm a more attractive option for civilizations that wish to maintain their homeworlds while expanding their energy capabilities. From an observational standpoint, detecting a Dyson swarm might be easier than detecting a Dyson sphere. A sphere would completely enclose a star, leaving only the infrared radiation of waste heat as a signature. A swarm, on the other hand, might partially block the star's light, creating a dimming pattern that could be detected by telescopes. These dimming events would be irregular and complex, reflecting the movement of individual collectors in their orbits. Advanced instruments like those used in exoplanet searches could potentially identify such patterns, providing evidence of a civilization building a swarm. The star KIC 8462852, also known as Tabby's star, has shown irregular dimming patterns that some have suggested could be caused by a partially constructed swarm. While natural explanations like dust clouds or planetary debris are more likely, the possibility of an artificial origin continues to intrigue researchers. The challenges of building a Dyson swarm are not insignificant. Coordinating the orbits of thousands or millions of individual collectors would require advanced computational systems and precise engineering. Maintaining the swarm over time would also be a major task, as collectors would need repairs, replacements, or upgrades. However, these challenges are not insurmountable, especially for a society with the motivation and resources to undertake such a project. Alien aesthetics. Could we misinterpret alien megastructures as natural? When imagining alien megastructures, the human mind often gravitates toward grand, intricate designs, things that stand out boldly against the backdrop of the universe. Gigantic spheres encasing stars, sprawling networks of reflective panels, or vast artificial habitats are common visions. But what if alien civilizations, whether by necessity, choice, or a perspective entirely unlike ours, build structures that blend seamlessly into their environments? Could these structures be so subtle, so well integrated with their surroundings, that we mistake them for natural phenomena? One of the biggest challenges in recognizing alien technology is our tendency to project human design principles onto the unknown. Earthly architecture and engineering are influenced by aesthetics, efficiency, and the physical limitations of our environment. We use materials that are accessible to us, and our designs are shaped by gravity, weather, and cultural preferences. However, an alien civilization may operate under entirely different principles. Their biology, planetary conditions, and technological capabilities could drive them to create structures that are unrecognizable to us. What looks like a strange asteroid, a faint gas cloud, or an unusually reflective planet might, in fact, be a carefully engineered construct. Take, for instance, the possibility of camouflage. Advanced civilizations may deliberately design their megastructures to avoid detection, either for self-preservation or to minimize their impact on their cosmic surroundings. If a civilization is concerned about the risks of being discovered, whether by hostile entities or simply by curious, less advanced civilizations, it might build structures that mimic the appearance of natural celestial objects. A Dyson swarm could be designed to resemble a dense asteroid belt when viewed from a distance. The individual collectors might be shaped like irregular rocks, with surfaces that scatter light in a way that mimics natural debris. Even without deliberate camouflage, the sheer unfamiliarity of alien design could lead us to misinterpret it. Imagine an immense network of energy collectors spread across a star system, connected by invisible beams of energy transmission. From Earth, we might see an unusual dimming pattern in the star's light, or a faint haze that doesn't fit neatly into our models of dust or gas. Without understanding the purpose or function of these structures, we might classify them as anomalies or unusual natural phenomena rather than artificial creations. A civilization with advanced control over matter and energy might build structures at the atomic or molecular level, creating a lattice of particles that manipulates light, heat, or gravity. They might create a vast, invisible web of nanomachines to harvest energy from a star, a web so fine and so evenly distributed that it looks like a faint cloud of gas. Our instruments might detect slight irregularities in the star's light or temperature, but without direct evidence, we could easily assume these effects are natural. A ring-shaped structure around a planet might look like a natural ring system, like those around Saturn. A massive habitat orbiting a star might be mistaken for an unusually large planet or moon, especially if it has an atmosphere or surface features designed to mimic those of natural celestial bodies. Such structures could even incorporate elements of natural objects, like using asteroid material as a foundation or blending with existing planetary rings. On Earth, humans often alter their surroundings to suit their needs, but we are increasingly exploring ways to work with nature rather than against it. An alien civilization might take this principle to an extreme, designing technology that harmonizes so completely with its environment that it becomes indistinguishable from it. They might construct habitats within hollowed-out asteroids, leaving the outer surface untouched. Ordinary-looking space rocks might have interiors teeming with life and advanced technology. Many of the tools we use to study the universe, such as telescopes and spectrometers, are calibrated to look for stars, planets, and galaxies, not for the potential fingerprints of advanced civilizations. As a result, we might overlook subtle signs of alien activity simply because we're not looking for them in the right way. Developing new methods to search for artificial structures, such as analyzing unusual energy patterns, light signatures, or gravitational anomalies, could help us identify megastructures that are currently hiding in plain sight. Arthur C. Clarke's famous adage, "Any sufficiently advanced technology is indistinguishable from magic," could be expanded to include the idea that a civilization millions or billions of years ahead of us might manipulate space, time, and energy on such a fundamental level that their creations blend seamlessly into the cosmic fabric. What looks to us like a supernova, a black hole, or a distant galaxy might in fact be the work of an advanced intelligence. This idea of imagining different alien aesthetics challenges us to think differently about the search for extraterrestrial life. Instead of looking for obvious signs, like radio signals or massive glowing structures, we might need to focus on the subtle and the strange. Patterns that don't quite fit, phenomena that resist natural explanations, or objects that behave just a little too perfectly could all be clues to the presence of advanced civilizations. By expanding our perspective, we open new doors to understanding the universe. Negative mass. Could exotic matter hold the key to warp drives? Unlike the kind of mass we encounter every day, negative mass behaves in ways that defy our intuition. Imagine pushing an object and instead of moving away from you, it moves toward you. This strange behavior arises from the idea that negative mass would have a type of inertia opposite to what we experience with regular positive mass. Negative mass is a concept that physicists have explored seriously, particularly because of its potential to unlock extraordinary possibilities like faster-than-light travel. In physics, mass is essentially a measure of an object's resistance to acceleration when a force is applied. For regular matter, this relationship is straightforward. Push a ball, and it rolls in the direction of the push. But with negative mass, this relationship flips. This bizarre property would lead to behavior that seems impossible in our everyday world. One of the most exciting areas where it might play a role is in the theoretical framework of warp drives. Warp drives, as envisioned by physicists like Miguel Alcubierre, rely on the ability to distort spacetime in a way that allows faster-than-light travel. In the Alcubierre drive model, a spacecraft would sit within a warp bubble that contracts spacetime in front of it and expands spacetime behind it. The ship itself wouldn't technically move faster than light within the bubble, but the bubble would allow it to traverse vast distances in a fraction of the time it would normally take. For the warp bubble to function, however, it requires exotic matter, substances with properties not found in any known materials. Negative mass is one such candidate for exotic matter. The unique properties of negative mass could provide the necessary energy density to create and sustain a warp bubble. Specifically, the negative energy associated with negative mass might counteract the immense energy demands of bending spacetime, making the concept of a warp drive more feasible. The Casimir effect demonstrates that negative energy can exist in certain situations. In this phenomenon, two uncharged parallel plates placed very close together in a vacuum experience an attractive force due to quantum fluctuations. The energy between the plates is lower than the energy outside them, effectively creating a region of negative energy density. While this doesn't involve negative mass directly, it shows that exotic energy conditions are not entirely beyond the realm of possibility. If negative mass exists, it could revolutionize our understanding of gravity. Regular mass generates an attractive gravitational force, pulling objects toward it. Negative mass, on the other hand, would theoretically repel both positive and negative mass. A spacecraft equipped with negative mass could potentially create a self-sustaining propulsion system. By pairing negative mass with positive mass, the two could push and pull on each other in a way that generates continuous motion without the need for conventional fuel. Despite the lack of direct evidence, researchers have explored ways to simulate negative mass in controlled experiments. In 2017, physicists created a system that mimicked some of the properties of negative mass using ultra-cold atoms. By cooling rubidium atoms to near absolute zero and trapping them in a specially designed laser field, the researchers were able to create a situation where the atoms behaved as if they had negative mass. While this simulation doesn't prove that negative mass exists in nature, it provides valuable insights into how such phenomena might work. Even if negative mass were discovered or created, controlling and manipulating it would require technological advances far beyond what we currently possess. The energy requirements for bending space-time alone are staggering, and the stability of a warp bubble is another major concern. Some models suggest that any warp bubble created with negative mass would be inherently unstable, collapsing before it could be used for travel. Others raise questions about the potential hazards of faster-than-light travel, such as the buildup of high-energy particles around the bubble, which could be released catastrophically when the bubble dissipates. If negative mass were used to achieve faster-than-light travel, would it break causality? According to relativity, faster-than-light travel could lead to situations where cause and effect are reversed, creating paradoxes that defy logic. These paradoxes are a major reason why many physicists remain skeptical about the feasibility of warp drives, even with the potential inclusion of negative mass. Still, their allure continues to inspire researchers and science enthusiasts alike. Even if negative mass remains a theoretical construct, the pursuit of understanding it forces us to rethink fundamental assumptions about the universe and explore new frontiers in physics. Do exotic particles from the early universe still linger today? The early universe was a place of unimaginable energy and density, a cosmic furnace where particles formed and interacted in ways we can only glimpse through theory and experimentation. Today, scientists study this ancient epoch to understand not only the origins of the universe, but also whether exotic particles from that time still exist, lingering as remnants of its fiery birth. In the moments after the Big Bang, the universe was an incomprehensibly hot soup of particles and radiation. As it expanded and cooled, familiar particles like protons, neutrons, and electrons began to form. But before this stage, the universe likely hosted a wide array of exotic particles, some of which might have properties vastly different from the particles we observe today. Theoretical physics suggests that some of these exotic particles could have decayed into more stable forms, while others might still persist, hidden within the fabric of space and time. One of the most compelling ideas comes from supersymmetry, a theoretical extension of the standard model of particle physics. Supersymmetry posits that every known particle has a corresponding partner, or superpartner, with slightly different properties. For example, the electron would have a superpartner called the selectron, and the photon would have a superpartner called the photino. These superpartners are generally predicted to be much heavier than their counterparts, which is one reason they haven't been observed in experiments yet. If supersymmetric particles exist, some of them might have been created in abundance during the early universe. As the universe cooled, many of these particles would have decayed into lighter, more stable forms, but some could still be around today. For instance, the lightest supersymmetric particle is often theorized to be stable, meaning it wouldn't decay over time. Such a particle could even explain the nature of dark matter. Beyond supersymmetry, other theories also predict exotic particles that might have survived since the universe's earliest moments. One example is axions, hypothetical particles proposed to solve a problem in quantum chromodynamics, the theory describing the strong nuclear force. Axions are predicted to be extremely light and weakly interacting, which would make them very difficult to detect. They are a prime candidate for dark matter, and several experiments are currently searching for evidence of their existence. In theoretical physics, magnetic monopoles are particles that carry a single magnetic charge, either north or south, unlike ordinary magnets, which always have both a north and south pole. Some grand unified theories predict that magnetic monopoles would have been produced in the early universe. If they exist, they could provide crucial insights into the conditions of the early universe and the unification of fundamental forces. Particle accelerators like the LHC aim to recreate the extreme conditions of the early universe by smashing particles together at incredibly high energies. By studying the resulting particle interactions, researchers hope to uncover evidence of supersymmetric particles or other exotic phenomena. At the same time, astrophysical observations are providing new opportunities to search for relic particles. Experiments designed to detect dark matter, such as those using underground detectors or sensitive cryogenic instruments, are constantly improving in sensitivity. These detectors are looking for the faint interactions that might occur when a dark matter particle collides with an ordinary atom. The data collected so far is helping to narrow down the possible properties of dark matter. Cosmic rays, high-energy particles that travel through space, also offer a potential avenue for discovering exotic particles. Some theories suggest that cosmic rays could produce signatures of dark matter or other relic particles when they interact with the interstellar medium. By studying cosmic rays with instruments like the Alpha Magnetic Spectrometer on the International Space Station, scientists are searching for patterns that might point to the existence of exotic particles. Certain types of exotic particles could have also left imprints on the CMB, providing indirect evidence of their existence. If we can detect and study these particles, they could reveal new laws of physics and challenge existing theories. They might even answer some of the most fundamental questions about why the universe looks the way it does and why we are here to observe it. Is there a final theory of everything, or are mysteries eternal? The search for a theory of everything is an attempt to create a single framework that can explain all the fundamental forces and particles in the universe, uniting the rules that govern the very small, quantum mechanics, with those that govern the very large, general relativity. For decades, physicists have been striving to uncover this ultimate theory, hoping to answer the deepest questions about how the universe works and why it exists in the way it does. Quantum mechanics describes the behavior of particles and forces at the smallest scales, such as atoms and subatomic particles. It is probabilistic, meaning it deals with likelihoods rather than certainties. General relativity, on the other hand, explains the force of gravity and the structure of space-time itself. It operates on a grand scale, describing the motion of planets, stars, and galaxies. Both theories are incredibly successful in their respective domains, but they don't align when applied together. This incompatibility has driven the search for a unifying framework that can bridge the gap. One of the most promising candidates for such a framework is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. These strings vibrate at different frequencies, giving rise to the particles and forces we observe. String theory is appealing because it naturally incorporates gravity into a quantum framework, something other approaches have struggled to achieve. It also suggests the existence of additional dimensions, which might help explain some of the universe's hidden complexities. However, string theory is not without its challenges. It has yet to make predictions that can be tested experimentally, which has led some critics to question whether it qualifies as a scientific theory at all. Its mathematical elegance is undeniable, but without observational evidence, it remains a hypothesis. Despite this, many physicists believe it holds promise as a step toward the ultimate theory. Another approach is loop quantum gravity. Instead of treating gravity as a force that emerges from vibrating strings, loop quantum gravity attempts to quantize space-time itself. It envisions space-time as being made up of discrete, tiny loops, much like a woven fabric. This approach has yielded intriguing insights into the nature of black holes and the structure of the early universe, but it too faces significant hurdles in connecting with observable phenomena. Beyond these specific theories, some scientists wonder whether the quest for a theory of everything might be misguided. Perhaps the universe is too complex to be reduced to a single elegant set of equations. Nature might not adhere to our desire for simplicity, and the answers we seek could be scattered across different domains, requiring multiple theories to describe different aspects of reality. But if such a theory were to exist, it would represent the culmination of centuries of scientific inquiry. It would answer questions about the origins of the universe, the nature of time and space, and the fundamental rules that govern existence. Some thinkers suggest that mysteries might always remain. Even if we discover a unifying theory, it might not be the end of the journey. Instead, it could open the door to new realms of inquiry that we cannot yet imagine. The history of science has shown that each breakthrough often leads to more questions. Newton's laws of motion seemed comprehensive until Einstein's theories of relativity expanded our understanding of gravity and space-time. Similarly, quantum mechanics revolutionized our view of the atomic world, revealing a level of complexity that classical physics could not explain. Testing theories that operate at the intersection of quantum mechanics and general relativity often requires conditions that are far beyond what we can currently achieve. Probing the extreme environments near black holes or recreating the high-energy conditions of the early universe in a laboratory are daunting tasks. Advances in technology and experimental techniques will be crucial for making progress, but there is no guarantee that they will yield definitive answers. There is also the possibility that human understanding is inherently limited. Our brains evolved to survive and navigate the world, not to unravel the secrets of the cosmos. We have made incredible progress through the development of mathematics and technology, but there might be limits to what we can comprehend. If the universe operates according to principles that are beyond our cognitive abilities, then a theory of everything might forever elude us. Science is not just about finding answers. It is about refining our understanding through observation, experimentation, and critical thinking. Even if a unifying theory were discovered, science would continue to explore its implications and applications. The pursuit of knowledge is an ongoing process, driven by curiosity and the desire to understand the unknown. Are we the first intelligence in the universe? The universe is about 13.8 billion years old. In that immense stretch of time, stars have formed, lived, and died, scattering the ingredients of life across the cosmos. Planets capable of supporting life could have emerged billions of years before Earth even existed. With so much time and space, why does it seem that intelligent life, if it exists, is so rare or elusive? The silence of the universe, often referred to as the Fermi paradox, looms over this discussion. If intelligent life is common, where is everyone? Earth formed around 4.5 billion years ago, and life began relatively early in its history. Simple organisms appeared within a few 100 million years of the planet cooling enough to support liquid water. However, it took billions of years for complex life to evolve, and even longer for intelligence to arise. The long, winding path of evolution shows how many variables must align for intelligent life to develop. It's possible that similar processes are happening on other planets right now, but are still in the early stages. If that's the case, humanity could be a kind of pioneer, one of the first intelligences to emerge in the universe. Earth benefits from a series of fortunate circumstances: a stable star, a protective magnetic field, and the right chemical ingredients for life. These conditions might be rarer than we assume. Even with billions of potentially habitable planets in the galaxy, the exact combination of factors that led to life on Earth could be an extraordinary rarity. If that's true, intelligent life could be exceedingly uncommon, and humanity might indeed be a cosmic anomaly. But rarity alone doesn't explain the silence of the universe. Even if intelligent civilizations are rare, the sheer number of stars and planets suggests there should still be others out there. Some scientists speculate that intelligent life might face significant challenges that prevent it from spreading across the galaxy or leaving detectable traces. These great filters could occur at any stage of development. For example, the transition from simple to complex life might be incredibly difficult, or intelligent civilizations might tend to self-destruct before achieving interstellar travel. If humanity has passed such a filter, we could be among the lucky few, or even the first, to do so. Alternatively, it's possible that the universe has seen other intelligences, but they no longer exist. Civilizations might rise and fall like waves, leaving behind no lasting evidence of their existence. If a civilization existed millions or billions of years ago, its artifacts might have eroded, been consumed by black holes, or otherwise vanished into the cosmic background. In this view, intelligence might not be a permanent feature of the universe, but a fleeting phenomenon. There's also the possibility that other intelligences exist, but are so different from us that we fail to recognize them. Humanity's understanding of life and intelligence is based entirely on our own experience. We assume that intelligent beings would use technology, build structures, and communicate in ways we could detect. But what if intelligence can exist without physical form? Or what if it operates on scales of time and space that are incomprehensible to us? In such cases, we might be surrounded by intelligence without realizing it. The universe is vast, and we've only begun to scratch the surface of what might be out there. The lack of evidence doesn't prove we're alone. It only shows that the search is incredibly challenging. Even if humanity is the first intelligence, that status comes with immense responsibility. As the first, we would have the opportunity to shape the future of intelligence in the universe. We could spread life and knowledge across the stars, becoming the ancestors of civilizations that might one day look back on us as their origin. However, being the first also means navigating uncharted territory. There's no guidebook for becoming a galactic civilization, and the challenges we face could determine whether we succeed or fail. On the other hand, if we're not the first, the silence of the universe might still carry a lesson. It could be a warning about the dangers that lie ahead, or a reminder of how fragile intelligence can be. What side of the argument do you land on? Leave your thoughts down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.